basically what's going on here? So these hyperedges are basically one has two nodes and another one has three nodes, right? That's usually how you deal with these. They don't necessarily know about each other, so you would kind of programmatically have to think about, okay, so I have a hyperedge that has three nodes, but are any of these other nodes? Maybe that's a way to do it, right? That you're like, are any of the other nodes like sort of related by another hyperedge? Because that would impose a constraint. And I think that is true for the case where they're nested and the case where they're not nested, because if they are nested, then it means that then I don't know what it means. Hmm. Because, you know, the thing here, right, is that if I know that this is one, hmm, this could still be one, correct? No, this must be zero because I'm in the green hyperedge. Hmm. So here I was documenting the rules. Oh God, things are just going crazy slow. Anyway, so be patient with me. I'm changing the machine soon, but it's just a disaster. Disaster. So the rule number one would be that how I would formulate it. So sort of if I know I am in a particular hyperedge, then I know the rest of the nodes in the hyperedge are true, right? And I know this is just a funny. It's not formal at all, but um, not nodes, but elements, right? That is important, because I don't know how to write the case that, you know, if you have this nested case, right? It's like if I'm like I cannot just say that, oh, I know this is one, so I can tell for sure that this is one. That is not true, even though I'm within the hyperedge. But this is because this hyperedge is embedded into a broader hyperedge, right? Um, so that is only true for like top level hyperedges, in a way, yeah. That is kind of like uh, top level hyperedge. Then I know the rest of the elements in the hyperedge are true. Like how would I don't know how would I formally describe these things, right? Are true. Because the hyperedge, that's the thing is the hyperedge, by just virtue of just the way it's defined, these hyperedges are just, you know, kind of happen to be independent and they all relate the nodes, not the hyperedges. Uh, mm, is there anything special about this stuff? Nested hyperedges? nested hypergraphs, hypercats. Maybe there's a better structure for me. You know what I mean? Maybe it's like a tree, right? You know what I mean? Maybe subgraph one, subgraph two. Like maybe it's rather a tree structure what I should use in this case. Uh, to be honest, I don't think so because there's also a lot of edge cases run like that might look like that, and I think that it's going to be not doable with a tree. It's just that we have to we have to. This is something that we have to yeah make sure that we can calculate efficiently so that we can say, okay, so for this hyper edge, like, am I, are all these contained into another hyper edge? And so that's kind of what matters, this kind of bubbling up. Yeah. Or kind of whenever I'm answering questions, whenever I ask the model to answer questions, right? And say, hey, I know this qubit is one, so what can you tell me about the other qubits? And I'm like, well, this is inside this hyper edge. But I can only tell that's true, right? If it's a top level. If it's inside another hyperedge, then I need to know what is in the other hyperedge, and then I need to decide whether that's something that I can infer or not. These seem to be the three cases I have. I have simply like hyperedges that are alone. I have hyperedges that kind of cut through, and I have hyperedges that are totally nested. Then there's of course another case maybe of hyperedges cutting through two levels of nestedness. Like, that would be incoherent if I would just kind of say, now what if these two are connected like that? Would that make sense? That would probably not make sense because it's inconsistent, right? Because if I know this is one, I know these are two ones, but then this hyperedge is something that is just invalid. So okay. Anyway, let's go. Let's go where I wanted to go, which is basically take a look at, yeah, so opening VS Code made no sense, and I'm gonna, I think, just, I'll keep it there, doesn't bother. It probably bothers, but whatever. Um, so let's take a look at these, and let's take a look at famous entangled states. Let's see if we'll get something interesting. We have the GHZ. These are interesting. Can be written as 0, 1, 1 tensor product plus 0, minus 1, 1 tensor product minus. How would I even go about writing something like these? Yeah, well, that's actually telling that if I know this is plus, then I know that this is 0 and 1. If I know this is minus, I know this is 0, minus 1, 1. Yeah, okay. So what this is just telling, but this is, yeah, but this is something that we can then kind of later on say, look, so I know the G, so let's start from what we know. So the GHZ is definitely like these. It's just like that. There's no secret in here. Of course, if I now ask the system, what if the top qubit is the plus state, but then I can transform these hypergraphs so I can then, this is another question. Yeah, this is another question. So this is but it's an answerable question. So that's easy. What are other famous quantum entanglements? So what are other things that we, it'll be interesting to see mixed entangled states. This is really generic. I want something quantum computing-ish. Bell states. Oh, so okay, what are they? Spin squeezed states. Oh, this is something else. This, I don't know. Known state. Okay. How are the other ones? So for 3 qubits there was the GHZ and there was another class of entanglement. 3 qubits entanglement. No, W states. Let's go through these ones. So Bell state is just just the upper part here, right? So what about the W state? So the W state is okay. So those are all the ones that are yeah, that they have these three. Okay, that's an interesting, cool circuit. That okay. So this probably will take a while. Let's see if that helps me clarify some stuff. So we have a state where, so what we know here, one way to specify these is that once we know that one is a one, right? Then we know that the other ones are zeros. So this is one way to, and that there's always one. So how will we do this? So we have 0, 0, and 0, 1, 1, 1. And I guess the thing is, yeah, I'm not so sure if that's a good blueprint to kind of start always with like mixing up all the states, right? But we'll see, because maybe if I would just follow the construction procedure, which I can try to do. Okay, there's a Y rotation. The angle is these. Okay. So, cool. Let's close the rest. So if I this could be pretty messy, right? Because if I know that this is a 1, then I know that these two are 0, right? So one way that I could do this is I kind of could make the circles and then, yeah. Could make kind of hyper edges, 1, 2, and then 3, and then pair it with the other one. So is there a cleaner way to do that? Another way would be that I know that if, for example, the top qubit is 0, right? It's kind of making it as a conditional. If I know the top qubit is 0, then I know that either one. So then I know that that either you have 0, 1 or 1, 0, right? So if the top qubit is 0, um, you know, what one could do something like that. It's cool because I see this quite some. So if so, then I know that this is the way. Is that correct? Does this make sense? Because you're basically saying, I know that if it's, first of all, I know that if I'm in one of these, the other one is not true because it's the same qubit, and automatically I know that this is a 0, right? Whereas here, but I'd still have to say, but I still have to say that if, uh, do I need another, hyperedge here? This is a pretty nasty, or complicated one to come out just out of the blue. Maybe, you know what, maybe this will actually help me construct it better. So if I open Quirk, because then I would still have to say that, you know, I can still kind of draw these, right? So I know that if it's 1, then this is 0, 0. That's the here, and if it's 0, then it's wider one of these. So and that's pretty messy in comparison to the G8 set, right? So what if I do a so a rotation of what is 2? What is this? Quadratwurzel von 2. Whatever. So what if I just, do I have to specify degrees? I think I have to specify degrees, right? So it's 109.47 degrees. Let's give it a test first, okay? So, oh, in radians, okay. Okay, cool. So it's 191. So I'll just say 191. No. 191. Cool. What am I doing? 191. There you go. And now I'm doing a control Hadamard, control node, and X gate. So control Hadamard, let's first see if this works. Control node and control node. and not gate. Yeah, there you go. There you go. That's the state that we have. So, what's the state here? So, okay, so it's like, okay, so this basically takes us into like a 1/3 of the 3/0 of 1/3 of 0 and 2/3 of 1. That's what this rotation does without any, like there's no relative phases. That's good. So this means, because I'm trying to, I know I said I wouldn't do that, but it feels like it's a more natural way. Maybe following the rules that I have, see if I can get to a result that I like, that it's better than this mess, and that maybe eliminates some new things. So I have 0, 0, and 0, and I have 1, 1. No, no, no. What am I doing? So we're starting with all zeros. So we're starting with all zeros, but then we do a rotation, which basically what the rotation would do is it would just kind of rotate the state, right? So I would really have a kind of like a 1/3 0 plus 2/3 of 1, and then 0 and 0. Awesome. Then I apply a control Hadamard. So the control Hadamard would tell me is like split the things apart, right? So split these two apart. So then now I have like, and I have to keep this like 1/3 of a 0, and then 2/3 of a 1. And now the rules would tell me apply Hadamard to the second qubit. The second qubit is the Hadamard is just the rule B, take a 0 into a plus state, take a 1 into a minus state. So that basically stays 0, and that stays as a 0 plus 1. That stays 0, and here we have our first hyperedge. And that is the first hyperedge. This means at this point in time, I know that if this is a plus state, this is a 1, right? So in this I can see that here if I do an axis control for the plus state here, I can tell that this is, yeah, so that this is, what? What? No. Okay, so the first weird thing is here. What? Why not? Why is this like that? 80 and 20. If this is the plus state, right? Okay, that's confusing. Oh, no, why? I thought that's the point, right? If this is the Hadamard, and okay, but I get why. It's because, yeah, because that control doesn't. So that control basically it there's a portion of the 0 that should be also counted. Is that correct? That is half plus and half minus, right? So it's actually, yeah, it's actually a half. So a half of these is, you know, 1/6, right? And so if I say 1/6 plus 2/3, then we get, yeah, kind of roughly 80%. So I think that kind of makes sense-ish. Yeah, this is the way it's represented. And again, if this being a 0 doesn't tell me anything about any of these, so that seems okay. The next step is a control knot down here. Now, this is an important rule. Okay, so now I got to split this farther, but I'm staying within this edge, right? So I'm staying So this is still like a third of a zero. It's still a 2/3 of a 1, and now I get a 0 plus a 1. This is what we're kind of doing as a mixture because it's an LCOM match, right? And now, but now it's a control knot. So yeah, okay. But basically what that means is that, yeah, that kind of stays the way it stays, isn't it? Uh, that stays the way it stays. It stays. So I can mix it up. I do this, but then this turns into 1 into a 0. And so the question is, what does it tell me now? This is an important question. Like after these control knots, if I do a control display here, yeah, you see, that is cool. Okay, that is an important rule. Because here I know it's a plus state, but after doing that, it stays mixed up. That's an important rule. So I don't rejoin things. Huh. Crazy. I don't rejoin stuff. So it stays like that. The control just mixes it up. I know that in some cases I shouldn't be doing these, but yeah, that's another edge case to look for, right? That control has just mixed things up. Fuck, why? Why? So so now this is what the control knot has done. No, of course. I'm stupid. Of course it does. That's not a special rule, man. That's not a special rule because it's a control knot. So it's gotten the 0 and it's gotten a uh, 0. Okay, give me a second. I'll be right back. It's all back there. Sorry for that. Um, cool. So where were we? We were here with this step here, the control X. Let's see if we get that right now. Well, for one, we'll need a 1 here, right? No. Whoops. There we go. Cool. Whew. Thought I had lost. I just wanted to go. So we'll need a 1 here. And now, okay, so now it's getting interesting. So now we have, well, this is only going to be the case, right? If it is 0, it can be 1. It actually will be 0. This we know for sure. It's a bit of a Bell state, right? In here, but then uh but then the truth is now, and now it's getting complicated, right? Which is like, does it include the 0 or it doesn't? I think it does. I think it definitely does. Because, and again, right, that doesn't mean that this is just, it's supposed to be a mechanism to help us answer questions. 0, 0, 1, 1. I think we'll end up with a really similar structure to the 1 here. It's just that I think I have a big issue when I try to do this from scratch with like trying to kind of cover all the cases with hyperedges, and I don't have to. That's the point. Because I mean, the next thing that happens is a control node between the first and the two qubits. In this case, oh, and by the way, what I was trying to do before is like that's obvious because a plus, right? If I'm controlling on a plus state here, it's a full match here, but it's an LCOM match here. So I actually, in order to answer the question, I have to separate these into two and then take. Yeah. Yeah, but still, into a plus, into a minus. Yeah, exactly. So there is a portion of zeros involved. Exactly. So now there is another C naught gate here, which basically tells me that, like, well, there's a full match here. And then the only thing that I have to do, because there are full matches here as well, is just change these. So that is an easy change. And note that now I'm basically ending up with what I kind of had here, right? So this will be a 1 in black, please. This will be a 1 and this will be a 0, right? So this is kind of what I had here. And then, yeah, and actually that's pretty cool, like it's now an X gate. And so this means, bam, I actually, yeah, so that's not needed. Oh, wait a second. This is wrong. I mean, oh, that's another technicality, but that's we're gonna solve this now, which I mean is like why I shouldn't have two zeros here. I want to avoid that. But okay, that is now a 0, and that is a beautiful 0 and a 1. Exactly. Now I want ideally, so that is the trick here, right? The technicality that I have here is that because I've had to separate these two, but I already had a 0 here. You know what I mean? Like that zero is redundant in a way. I already have a zero, so the thing is when I do the splittings here, I have to think, okay, so I split 0 and 1, but I already have a 0. Um, and the trick will be here that I somewhat have to make sure that the amplitudes are okay. Like I think that's the thing. I think that is just becomes irrelevant, right? And I wanted to do another test. Wait a second, which is like, is this mixture? So one thing that I did before in my previous model is that I was keeping the weights in the hyper edges, right? Because I was interpret it was the interpretation was different. So, but now I keep them here. What I wanted to check if it's something that it's accurate in terms of what one would see here. Yeah, it is accurate in a way that we can know the proportions, but it's incoherent, right? So this means there's 33% chances we get a zero and 66% chances we get a one, and like you know you see that here as well. But it's yeah, that's cool. So that makes sense. So these amplitudes or these probabilities kind of stay there. Um, the question is like, does this keep being 50-50? Because that is also an important technicality after all these. Like, what is the state of this qubit? Yeah, there you go. There's more zeros than ones. And I think that's crucial. That is crucial because this is okay, so this is what's happening here, right? So when I have to do the split, um, when I have to do the split, right? So that originally was so that originally was a zero, then we turned it into a zero and a zero plus one. So it's like 50% and 50%, right? But then, but from these 50%, these kind of halves go here. So it's actually uh, 66, 2/3 and 1/3. That's literally there's like, yeah, two zeros and one one. So actually, actually here you kind of have like a 2/3 and 1/3. Shouldn't it be the other way around though? Shouldn't it really be the other way around? Why doesn't these change after the control node? That's interesting. Hmm. Thought it should change, shouldn't it? Well, no, you still have 2/3, and you just you just change the size, but you still have two. Yeah, yeah. Hmm. So wait, so the amplitude stays. That is something weird, actually, because Here it does change, right? After the NOT gate. But then why doesn't it change? Why doesn't Quirk change it? After these. Ugh. Ugh. Well, that makes sense, right? Because we know that it's 0. So this is before the NOT. Then this is got to be 0. Do we know that? Hmm. There is a lot of things which confuse me right now. So do we know that if this is 1, then this must be 0? Like, how? Interesting. Because, okay, so this is, yeah, this is definitely next level for next stream. I gotta go now, but this is definitely next level. Because here it's just awkward, right? Because I'm like, if it's 1, I must be able, and that's kind of what this edge here was the purpose for, right? If it's 1, I must be able to say that this is 0. Whereas if I keep doing it like that, just because I merge these two things, which kind of tells me that maybe I just shouldn't merge the things. Because essentially, if this is 0, then I know this is a mixture, right? So if it's a 1, I know it's not a mixture, but then what is it? Like, it cannot be a mixture. Like, I mean, the answer was here, right? I just got rid of it. The answer was here. Okay, so yeah. So, but then you wouldn't have amplitudes in this case. You just kind of have uh, complicated, complicated. This thing with the amplitude is going to be complicated as well. Let's see. Okay, but that's the example that we're working on now, because that's what's gonna that's stretching the model. The W state. Cool. This part makes sense. When it's 0, it's kind of like, yeah, that was even intuitively what I had built before, right? So it's just a matter of how do I answer the other questions, like what if it's a 1, right? How do I tell that it's certainly a 0? I know it's not a mixture, so I know it's either, well, maybe. So the thing is, I know it's not a mixture. I know it's not 1, 0, nor 0, 1. So it's going to be either 0, 0 or 1, 1. So that is maybe the only thing that uh, I'd be missing to clarify here. Because that would still be, I'd still be able to answer the question, like what is then the value of this qubit? I know that it's none of these. So it could still be 0, 0, 0, 1, 1, 1. So why not 1, 1, 1, 1? So why not 1, 1, 1, 1? That is the, like, how would I be able to answer this question from this model? My first answer is that it doesn't, but let's see. Cool. See you on hopefully Thursday. Bye bye.